In Chapter 7, we start to go over some more advanced topics where trigonometry can be applied. In this class, we're really just going to introduce these topics, and then they most likely will be things that you'll see in more depth later on. Most of them you won't see until a bit later. The ones that you might see earlier are these last two sections deal with something called vectors. And those you'll typically see in a lot of physics classes. So you might have even encountered vectors already in some of your physics classes if you've taken any of those already. We are going to see some formulas. Specifically in section 7.3 we're covering something called de Moivre's theorem. And in 7.5 we cover something called the dot product. And I just want to give you a heads up that those are two formulas that you actually have on your formula sheet for the class. So in this class, you don't need to memorize them, but I just want you to know when to use them and then how to use them. So let's get started with the first section, which is on something called polar coordinates. Okay, so what the polar coordinate system is it's an alternate coordinate system to the typical rectangular coordinate system. So an ordered pair in the rectangular system is listed as xy, where something like if you have 4, 5, the 4 indicates the x value, the 5 indicates the y value, and then you find where they overlap, and that's your ordered pair. So with the polar coordinate system, we're actually changing that up a little bit. So the ordered pair is r, theta. So r tells you the radius, and theta tells you the angle measurement. So for example, if you had something like 45 degrees, 2, to graph that on the polar coordinate system, you would first go and find 45 degrees. So that's rotating from the 0 up to 45 degrees. And then the r value is that radius. So if you notice that the coordinate system here is measured by the angles that go around, and there's also these circles. So you have a circle of radius 1, and then 2, 3, 4. And so the radius is how far out you go. So in this case, that would be radius 2. So that would be right about here, would be the point on that graph. The other thing to note is just, usually we call this 0, 0 in the rectangular coordinate system the origin. And the same spot essentially on the polar coordinate system is called the pole. Okay, let's look at a couple examples here of just graphing. So the first one, we want to graph 1, 3 pi over 4. So that tells us our radius and our angle. So the 1 is telling us that we're going to be plotting something on this circle on the inside with radius 1. And then at the angle of 3 pi over 4. So you could convert 3 pi over 4 if you wanted to degrees, but you don't need to. And then if we go ahead and find that angle measurement here, I'm just going to put a point that intersects that line and the radius 1 line. So it would be right about here. Okay, so for the other one, we've got a negative value. So when we're graphing polar points, if the angle was measured as a negative, that would mean the same thing as if we were graphing an angle in standard position. So a positive angle measurement means we rotate in the counterclockwise direction, where if we did have a negative angle, we could just go ahead and that would mean to rotate in the clockwise direction. Radius being negative is a little different. So first I'm actually going to go ahead and find where pi over 3 is on our graph. So pi over 3 is right here. So if we were going to plot the point, let's say 2, pi over 3, that would get plotted where we find the intersection of this angle, pi over 3, and radius 2, which would be right here. And I'm going to zoom in a little bit right now. So this is the point. Well, actually, since I zoomed in, just write it again. 2, pi over 3. So what does a negative radius mean? A negative radius means that it's going to be on the value of 2. You could look at it as being, it's a rotation of 180 degrees. But actually, I think a better way to look at it is we go in the reverse direction. So if we follow this line, and instead of, let's see, normally we go out towards that angle. If it's a negative pi over 3, we follow that line in the opposite direction. So that's considered -2. So this point right here is actually -2 comma pi over 3. So just think about if you have a negative radius that you're actually going to measure the radius like moving backwards instead of forwards. And this kind of also brings up another point which we're going to actually look at in the next example, but I'll just mention it now. With polar coordinates, there are lots of polar coordinates that would end up in the exact same spot. So you might notice this point here could have been written differently. So we could have written it as 2 comma 4 pi over 3, and that would have landed at the exact same spot. So this can happen a lot with polar coordinates, where the same coordinate ends up in the same spot. I guess I should say where a different coordinate, or at least it might look different, ends up in the same spot. And it has to do with that sort of repetitive nature of angles, that we could find coterminal angles. So let's move on to the next example. Okay, here we're given another point, another polar coordinate. In this case we have 4 comma pi over 12. And we actually want to find 4 other polar coordinates that represent the same spot on our polar graph. And we're going to write 2 of them with a positive value for r and 2 of them with a negative value for r. So first I actually want to just graph this point so we can kind of visualize what's going on here. So pi over 12 means we're dealing with this line, a radius of 4, and it's positive, so then I'm going to move out 4 on that ring there. Okay, and then this is our point, 4 comma pi over 12. Okay, so let's first work on finding 2 other points with positive r values. So basically that means the r is going to be the same, but I want to find another angle that would work. And this, really what we're going to be doing is just finding coterminal angles. Because as we know from before, a coterminal angle is an angle that's going to land in the same spot. And we find them by adding or subtracting a full rotation. And you could do that more than one time. So what I'm going to do here is, let me just write down, we're starting with pi over 12. So there's actually more than one answer that I could get, because for at least the way this question is worded, it's not saying I have to use a specific angle. It's not saying it has to be between 0 and -2 pi or anything like that. So probably what I'll do is I'll say, let's take pi over 12 and do 1 full rotation, because that would be, this angle that we have here. If I add 2 pi, it'll just bring me right back to that same spot, so it's going to land on the same point of the graph. So I'm going to do pi over 12 plus 2 pi. And something that you're probably pretty familiar with now is that if you are working in radians, common denominators help out a lot. So in order to add 2 pi, I'm going to make that actually 2 pi over 1. I want to get a common denominator, so I'm going to multiply it by 12 over 12. So we've got pi over 12 plus 1 full rotation, written in common denominator form, is the same as 24 pi over 12. So I get 25 pi over 12. And that's what I'm going to plug in for this first answer. 25 pi over 12. So I could actually do the same thing. I could take this angle, 25 pi over 12, and I could add another 2 pi. And that would give me my other answer. But I'll just go ahead and actually do subtraction just to show that subtraction works as well. So if I take pi over 12 and I subtract a full rotation, this case, since I already found the common denominator, I'm just going to write 2 pi as 24 pi over 12. So if I look back at my graph, that's just saying, okay, well, if I have pi over 12, but if I subtract, get rid of that arrow, it's going to bring me back to the same spot, and so that point's going to end up in the same place. So if we subtract it, we would say that's going to be negative 23 pi over 12. So another point would be 4, and then negative 23 pi over 12. So here are two answers where the r value is positive, and now let's find two answers where the r value is negative. And so if we think about that last example, when we have an r value that's negative, I'm actually going to go along the line, and the angle that we're going to need here is actually 13 pi over 12. And because if we had the angle of 13 pi over 12, and I'm just going to go ahead and write that, negative 4 comma 13 pi over 12, that would mean we'd go to the rotation of 13 pi over 12, and instead of going out, we would actually go in the reverse direction, which would lead us to that point we already had. So this is one ordered pair, one answer that will work, where it's going to end in the same spot, but now it has an r value that's negative. If, let's say, you didn't have a graph like this, where it happens to show you all these different angles, you can find that by starting with your angle, which we had pi over 12, and adding pi. Because if we add pi, that's going to give us that 180-degree rotation. And so if I got a common denominator here, pi is the same as 12 pi over 12, which is where 13 pi over 12 comes from. So let's find one last angle. And so basically, since we want this, not angle, but polar coordinate, since we want the polar coordinate to be a negative r value, that means it's going to have to be a negative 4 again. But now we need a different angle value. And so at this point, we're actually going to do coterminal angles again, because in order for it to end up to be on the spot here, where we had our 4 comma pi over 12, it basically needs to be the same thing as the negative 4 comma 13 pi over 12, but we're going to use a coterminal angle instead of using 13 pi over 12. So for that angle, now I could add or subtract one full rotation, which would be 2 pi, and that would give me my answer. I'm going to go ahead and write this down as 13 pi over 12 plus, I'm going to do adding one full rotation, 2 pi, which I'm going to rewrite as 24 pi over 12, and then we add these together. And that gives me my last angle value, 37 pi over 12. So all 4 of these points end up in that same spot, and there's an infinite number of points that could end up in the same spot. We've just found 4 of them. Now what we've got here is some formulas that help us with polar coordinates, specifically being able to convert back and forth. So we can have something in rectangular coordinates, convert it to polar, and vice versa. So the thing about these formulas is these are really not new formulas. These are the exact same things from chapter 4, where we talk about just the definitions of the different trig functions, and we use either triangles or circles for that. So I'm going to go and look at it from the triangle perspective, which is just that if we have an angle in standard position coming from that 0 line, the x is the same thing as the adjacent when we're talking about trig definitions, and the y is the same thing as opposite. The r value is our hypotenuse. And so we can use that because if we had a coordinate in polar form, we could convert to rectangular using these formulas. And I guess if I rewrote these formulas, they're just because the fact that cosine is equal to adjacent over hypotenuse, which is x over r, and sine is equal to opposite over hypotenuse, or y over r. So if you just multiply those by r, that gets you to these equations here. So these are not new equations. Those are just based on the definitions of sine and cosine. But so if I know what r is and I know what theta is, I just have to plug those values in, and from there then I can find what the equivalent x and y are if I wanted to convert from polar to rectangular. There's different formulas that we use to convert from rectangular to polar, but they're still just based off of the definitions that we've already seen. So one of them we're going to use is basically the Pythagorean theorem. So we can use that to find the r value if we know, if we're given x and y. So the idea is, here if we're given x and y, we want to find r and theta. So we can find r by using the Pythagorean theorem, and we can find theta by using this fact, the fact that tangent is equal to opposite over adjacent, which is the same thing as y over x. And the last step from here, if we actually wanted to figure out, well, what is theta, like give me an angle measurement, we could just use the inverse to say that tangent inverse of y over x will give us our answer for theta. So let's try some examples. Okay, so for the first one, we're trying to find the rectangular coordinate, and it's good to note that what we're given is polar. Sometimes it might not be obvious, so we want to make sure we know which one we're given and what we're switching it to. So if we're trying to find the rectangular, that means we need x and y. And we're given that r is equal to 6 and that our angle is 2 pi over 3. And so to find the rectangular coordinates, we're going to use the definitions for cosine and sine. So I'm writing the original definitions down, but you may be able to just jump right to the fact that x is equal to r cosine of theta and y is equal to r sine of theta. And now we just plug in our values. So r is 6 and theta is 2 pi over 3. So y is equal to 6 sine of 2 pi over 3. And so what we want to do is we actually want to evaluate cosine and sine of this angle 2 pi over 3. I'm going to go ahead and just draw a quick diagram here. So 2 pi over 3 falls in quadrant 2, where the reference angle is pi over 3, and then I'll fill in the sides. So pi over 3 is the same as 60 degrees. So across from the 60 degrees goes the square root of 3. That makes the adjacent 1 and the hypotenuse 2. That's one of our special triangles. Once I fill in all the values based on the reference angle, I just check all the positive negatives for each one. So based on this quadrant, the x is moving in the negative direction, the y is moving in the positive direction, and the hypotenuse is always 2. So if I go ahead now and just plug this in, we've got 6 times cosine of 2 pi over 3, which is going to be negative 1 over 2. And sine is going to be positive square root of 3 over 2, which gives us negative 3 for the x value and positive 3 square root of 3 for the y value. So putting it all together, then the final answer is that this polar point, 6, 2 pi over 3, is the same as a rectangular coordinate of negative 3, 3 square root of 3. One thing that I think is really good to check with your answers here is you can just check that it's in the right quadrant too. 6 and 2 pi over 3, well, I've already kind of talked about 2 pi over 3 is in quadrant 2, And if we went out to a radius of 6, we'd get some point. And we can kind of see if this answer we got makes sense here, which is that it makes sense that the x would be negative and the y would be positive. So that sort of checks out. Okay, let's try to go in the other direction now. So now we want to find the polar coordinates given 3/4, which is in rectangular form. So that means we know that x is equal to 3 and y is equal to 4. So to find our r value, we can use the Pythagorean theorem. X squared plus y squared is equal to r squared. So technically the r in this case could be positive or negative, because we've talked about what that means if the r is negative. I think it's easier to just keep the r as positive, so I'm going to leave it as positive and then just find an angle that's going to work with that value. So my r value is positive, and now I need to find my angle value, theta. So from there we use the fact that tangent of theta is equal to y over x. So in this case, that means tangent of theta is equal to 4/3. So we can use inverse tangent to find our angle. So if we plug that in, we get an approximation, and I'm going to talk about what we might do with something like that. So we've got 53 about 0.13 is our angle measurement. One thing we do want to make sure that we check, because we want to be careful, because when we're dealing with the inverse functions, when it's tangent, and in this section we're only going to be working with inverse tangent, so that's what I'm going to talk about. Not the other ones. Inverse tangent will only give you an answer in one of these two quadrants. It's basically giving you a reference angle. It's giving you a positive reference angle if the answer is positive, and that would put you in that first quadrant. And it's giving you a negative answer if the tangent value happens to be negative. So what you want to know, though, is that you're given this reference angle. And if your answer, though, should have been in something like quadrant 2, you just need to work backwards to convert that reference angle to the actual angle. Keeping in mind, like let's say if it was going to be in quadrant 2, a reference angle would be here, 53.13. So to figure out the actual angle, we could do 180 minus that. That in, and that gives us about 126 degrees, 126.9, I guess. I'll round it too. But if we check again to see what was the angle we were working with here, we were working with 3/4, which, you know, we could plot 3/4. It would be this point right here. So that tells us that our answer is in quadrant 1. So this is a case where the reference angle is the same thing as the angle. So I can go ahead and write my answer down for this one. And I'm actually going to write the answer two ways. So I'm going to write it one way as 5, 53.13 degrees and 5, tangent inverse of 4/3. These are both correct. The difference, though, is that this first one is an approximation. So if you were trying to find an approximation, typically you'll be instructed to round to a certain number of decimal places. This one I left it open. I didn't really specify whether to give an exact or approximate answer, so that's why I want to show both. But this would be if you were trying to find a decimal approximation. If you were trying to find the exact value, that means when you apply the inverse, if you just get, like when I plugged it into the calculator, I got the decimals that just kept going. That tells me, okay, if I cut this off at some point, it's going to be an approximation. So if I need the exact answer, then I just have to leave it in that inverse form. Like in this case, 5, tangent inverse of 4/3. Both of those I would say would be the correct answer for this one. So besides just plotting points, you can actually get the same graphs in either coordinate system. And so what I have here, kind of sort of, it's not side by side, but one on top of the next, is here. This is basically two graphs of a vertical line, the same vertical line. It's just one is rectangular coordinate system, and therefore the equation is written in rectangular form. And you can actually graph that same graph in polar coordinate system using a polar graph. So notice that the equation itself is different because you're working with a different coordinate system. And then the other graph is actually the graph of a hyperbola. And one's in rectangular and one's in polar form, but the graphs themselves are the same, like if you took away the actual coordinate system. And so you can actually convert back and forth. So just like you can convert an ordered pair, like we just did here, for example 3 and example 4, you can also convert equations to be from rectangular form to polar form. So that's not really something I'm going to have us look at in this class, but it's something that you could do, and the way that you would do it is by going back to the same things that we looked at to convert the ordered pairs, using these formulas here.